And let me introduce our first speaker briefly. So our first speaker is Ashley Cook from Max Planck Institute for Complex System. So she got bachelor and master's degree from University of British Columbia under supervision of the professor Marcel Franz. And she got PhD from University of Toronto, Arun Paramekasti. And after she did some postdocs from University of Chile and UC Berkeley, she's now moved to the, she recently moved to Max Planck Institute, and she's now research group leader of both Max Planck joint research group leader of Max Planck Institute for Physics of Complex System and Chemical Physics of Solid. So she has done many important research in the field of topological phase of matter, such as like a spin-orbit coupled system. Also, I noticed some important work in higher order topological phase and skyrmion phases of matter. Today, she's gonna talk about topological skyrmion phases of matter. And actually, please, you can go ahead.
Thank you very much for the kind introduction. And thank you very much once again to the organizers for inviting me. It's an honor to be here with you. So as a brief overview of the talk, I just want to give some motivation and background for the topic of the talk, which is the introduction of a set of previously unidentified topological phases of matter into the literature that really are characterized, I would say, by skyrmions forming specifically in the ground state spin texture over the entire Brillouin zone, even when you have other degrees of freedom in the ground state besides just spin. And I'll tell you about how to construct various toy models for the simplest of these skyrmion phases in both 2 and 3 dimensions. And one nice thing is, after I introduce the 3-dimensional phase, I can tell you about one of the bulk boundary correspondences that are known of so far for these topological phases, and serve as one opportunity for experimental detection. And then I'll talk briefly about a second bulk boundary correspondence before moving on to specific realization of 2 different kinds of topological skyrmion phases of matter in superconducting strontium ruthenate tight binding models. And this gives me an opportunity to tell you about one of the most interesting parts of the work, which is the fact that even for effectively non-interacting systems, while respecting the symmetry, protecting the topological phase, you can have 2 different kinds of topological phase transitions. So there's type 1, which occurs with the closing of an energy gap. And then there's actually type 2, which occurs without the closing of an energy gap. And I'll explain instead what happens to destabilize the topological invariant. And the second one, for those who are very specialized, you'll realize that this is quite surprising. And so I'll discuss the broader implications of this work. And so the earlier part of the talk is basically focused on a more recent archive entry that is much more pedagogical. I find that quite funny than the earlier work, which first introduced these topological phases. So briefly, I just want to acknowledge my graduate student Shui, who did a huge amount of work on this first project that I'll discuss, as well as Li Kunqi, a postdoc at PKS, who also made some very nice contributions. All right, so just as some quick motivation. So this is a conference on solitons, but maybe one of the realizations of solitons in condensed matter systems that people are most familiar with are actually the realization of skyrmions in magnetic systems over real space. So just very briefly, these are magnetic textures in real space that are topological in a certain sense. A simple example can look as follows. And basically, you can think about mapping these magnetic moments based on their orientation to the surface of a 2-sphere. And you would see, for instance, for this texture shown in subpanel C, that the moments wrap a 2-sphere, in this case once. And more generally, these skyrmionic textures, at least simpler cases, wrap this 2-sphere some integer number of times. And you can think of these textures as topological in the sense that you would have to poke a hole in this texture by having the spin or magnetic moment go to 0 in magnitude, basically, somewhere in this wrapping on the two-sphere in order to change the number of times that you wrap the sphere. And this has been a huge area of research, for quite a while. People are interested in these, potentially as a very dense form of data storage, as one example. People are also interested, for instance, in the topological Hall effect, which I'll mention briefly in a following slide. So to understand where that topology is coming from in a certain sense, we can think about a continuum model that realizes those real space skyrmions. So basically, you can write some Hamiltonian in terms of the magnetization vector n as follows, where here we have an exchange coupling term, a term that is allowed as a result of breaking of inversion symmetry, the Zhalozhinsky-Maria term, as well as an applied Zeeman field term. And the basic idea is that a model like this can serve as a mapping from projective real space. So at the simplest level, you could think of this as punctured real space with a hole in it, to the two-sphere when you are computing this magnetization vector. And this is actually contractible to a mapping from the two-sphere to the two-sphere. And then we can actually determine the topological classification for a simple model of this kind in terms of a homotopy group of spheres, in this case, pi2, S2, which gives us integer classification, which tells us there are integer distinct wrappings, basically, of these skyrmions on the two-sphere. And yeah, basically, if you want to transition between one or the other, you have to poke this hole in the spin texture. And we can actually characterize the number of times we wrap the sphere in terms of this topological charge, which can be expressed as follows in terms of that magnetization vector. And one interesting thing I want to point out here is there's really an emphasis in study of these real space skyrmions on the magnetic textures in the bulk, unlike in the case of phases of matter that I'm much more familiar with, which are the topological insulators, for instance, in which case there's a very strong emphasis on bulk boundary correspondence. The idea that you could have, say, in this case, three-dimensional bulk for a topological insulator protected by time reversal symmetry, you could have an insulating bulk and you could compute some topological invariant for that bulk. And if that takes a non-trivial value, then if you have open boundary conditions in some direction, you can expect topologically protected gapless surface states, such as the Dirac cone surface states of the 3D TI protected by time reversal symmetry. And this, at least for me, brings up the question of when can spin skyrmions specifically have more direct consequences analogous to bulk boundary correspondence. So there is a sort of bulk boundary correspondence due to real space skyrmions, but it's much more indirect, where basically the topological magnetic texture in the bulk is kind of used as a base from which to realize various bulk boundary correspondences. So the best known example is the topological Hall effect, where as a result of strong Hund's coupling, itinerant electrons moving around against the background of this magnetic skyrmion texture pick up a Berry phase. And then you basically realize a quantum anomalous Hall effect or just an anomalous Hall effect as a result of the real space skyrmion. But you see how this is sort of indirect, basically. And there's also been some work, I think, trying to realize topological magnon phases using the real space skyrmion as just a platform. In that case, again, it's like you're just realizing some other topological phase using the real space skyrmion, which has a bulk boundary correspondence. So the one question for me is just like, when can you more directly have a bulk boundary correspondence due to a spin skyrmion? So there is one example that we're aware of already, which is actually when you have a spin skyrmion in momentum space over the full Brillouin zone, rather than, for instance, just on a Fermi surface, which is something that people who study superconductors are much more familiar with, mappings from the Fermi surface to, say, an order parameter space. Instead, if we consider, for instance, a simple two-band block Hamiltonian, specifically, well, in this case, the simplest case is two bands, such as the following one for a Chern insulator phase. If we plot the ground state spin expectation value texture over the Brillouin zone for the case of a non-trivial Chern number, we will see a skyrmion basically form over the Brillouin zone. So I'm just showing a very cute example from past work with my doctoral advisor, Professor Run Paramakanti, for an interesting case of a two-band model that actually realizes Chern number ±2 for individual bands. In this case, the first Brillouin zone is highlighted by this black hexagon, and you see that at the corner of the Brillouin zone, the spin is pointing down. As we move towards the center of the Brillouin zone, the spin tips into the kx-ky plane and actually wraps by 4 pi before pointing up at the center. So it's a really cute example of wrapping this block sphere twice. And in this case, the physics is arising because our block Hamiltonian serves as a mapping from some d-dimensional torus, in this case, the 2 torus, to the 2 sphere when we compute this ground state spin or pseudospin. And because of properties of some lower homotopy groups, basically, this is contractible to mappings from the 2 sphere to the 2 sphere. And so again, we can use this non-trivial homotopy group that we saw previously. And a key point here, though, is that this skyrmion number is not in general equal to the total Chern number. So what happens more generally is that we have to think about skyrmions instead forming in the ground state, the texture of the projector onto occupied states over the Brillouin zone instead. And it happens that in the case of that 2-band block Hamiltonian, that is the spin texture, but more generally, it's a different quantity. And basically our classification of topological phases, such as the topological insulators or topological semi-metals, things like this, it's ultimately based on a classification scheme considering mappings from the full Brillouin zone to what's called the space of flat-band Hamiltonians, or basically space of projectors onto occupied states. So this is work by Shinsei Ryu and Andreas Schneider. Basically, it's making use of this, what's called the flat-band limit assumption. So this is the idea that if you start with some dispersive Hamiltonian with some number of filled bands, with some set of values for different topological invariants. In the simplest case, it could be just one invariant, but more generally, things are so complex, you should consider possibly having a set. And the idea is that if you adiabatically deform this system to some flat band counterpart, so that is without closing the bulk gap and without changing the occupancy of the bands, while respecting the symmetry protecting the topological phase in the effectively non-interacting regime only, then you're guaranteed that the topology, the values of each of those topological invariants remains unchanged. And so you can characterize the topology of a variety of dispersive Hamiltonians in terms of the topology of just the flat band Hamiltonians. And in this case, we can still think about computing winding numbers, different skyrmion numbers, basically, but now basically as the winding of this projector onto occupied states. So the key question, I guess, of this work is instead, when can we have ground state topology that's characterized by spin skyrmions beyond this case of the 2-band block Hamiltonian, or perhaps like an SUN block Hamiltonian? When can we have this topology in the ground state associated with spin rather than projectors? And this really leads to the question of when can you have a spin skyrmion, even if you have other degrees of freedom in your ground state, such as an orbital degree of freedom, because this is the case where the projector topology becomes distinct from the spin topology. So it's actually possible, and this is basically what these topological skyrmion phases are. They are phases realizing spin skyrmions in a way that leads to a very direct bulk boundary correspondence, familiar to us from study of topological insulators. Basically, if you have a generalized particle hole symmetry, which corresponds to a generalized particle hole operation C prime, where this operator is the product of the particle hole operator, where c squares to -1 and spatial inversion, then you can actually realize these spin skyrmions in the ground state, even when you have other degrees of freedom, such as an orbital degree of freedom. What's really nice is this product symmetry naturally suggests we should look for this sort of physics in centrosymmetric superconductors, the idea being that they have particle hole symmetry and spatial inversion symmetry individually, and then also the product symmetry. So for a block Hamiltonian to have this symmetry, it must satisfy the following relation, where J takes the following form in terms of an n by n identity matrix. And then if you can determine the topological classification of these Hamiltonians, at least based on mappings from the full Brillouin zone to the space of projectors or flat band Hamiltonians, to be the following: pi2 sp2n over un in the case of a two torus, where here sp2n is the compact symplectic group, which is the intersection of the complex symplectic group and the special unitary group, and un is the unitary group. And for the projector topology, we get integer classification. But a key point here is actually that this quotient can act on other quantities besides the projectors. Other quantities have the appropriate symmetry to be, acted upon basically by this quotient. And in fact, in this case, spin does. And you could see this, from the structure of the operators for spin, which I'll show in a moment for a simple case. You could get some intuition for this, thinking about the fact that the compact symplectic group is the intersection of this complex symplectic group with the special unitary group. And a really important point is that in general, spin is acted upon by this quotient, but not orbital or total angular momentum. For instance, if you have crystal field splitting that effectively reduces the symmetry of those quantities, they would be instead acted upon by something else. And there are cases where the homotopy groups associated with those quantities are trivial. And for spin, it's non-trivial. And you can get basically very interesting physics in this case. One thing, just for some intuition, if you consider the n = 1 case, then sp2 over u1 is isomorphic to su2 over u1, which is isomorphic to the 2-sphere. So for n = 1, we kind of collapse back down to the 2-band case that I was showing you previously. So this is a sort of generalization of an SU2 model. So I was saying that you can have very interesting physics if you have, for instance, non-trivial topology associated with the spin, but not, say, the orbital or total angular momentum. So basically, first of all, when do we expect a stable topological phase associated with the spin skyrmion number? Basically, if the spin is finite in magnitude everywhere in the Brillouin zone, the idea being that then if you change some parameter of your Hamiltonian by some small amount epsilon, if epsilon is sufficiently small, then your spin vector will remain finite in magnitude everywhere in the Brillouin zone. And so your invariant, the skyrmion number, is unaffected by sufficiently small perturbations. This is our broad, loose definition of a topological phase. And what's really cool is that then we can think about destabilizing this skyrmion phase, spin skyrmion phase, by having the magnitude of the spin go to 0. And the key point is that can happen in 2 different ways. So the first way is just that we have a closing of the bulk energy gap. But the other thing is, if we have non-negligible atomic spin orbit coupling and a suitable additional degree of freedom, like an orbital degree of freedom, then the spin can actually go to 0 in magnitude somewhere in the Brillouin zone without the closing of an energy gap, even in an effectively non-interacting system, while respecting the symmetry protecting the topological phase. So this is the basic intuition behind the type 2 topological phase transition, which is actually quite important, as I'll talk about further later on. So now I can talk about toy models. It's actually very easy to construct toy models for these phases, at least at the simplest non-trivial level, which is n = 2. So in the case of n = 1, the spin skyrmion becomes the projector skyrmion. But for n = 2, they are 2 different quantities, and they can decouple from one another. So at the simplest level, if you're looking for a non-trivial spin skyrmion for the ground state at the 4-band level, you can actually bootstrap off of those results for 2-band block Hamiltonians, basically constructing the simplest toy model as block diagonal and including the 2-band block Hamiltonian for a Chern insulator and its C prime partner. So just as some quick intuition for you, C prime acts in almost the same way as C, except you do not take K to minus K. So that's why you do not see minus KX minus KY here. So again, I'm just showing one example block Hamiltonian for a 2-band Chern insulator here that could be used for the construction. And basically you can compute the ground state spin expectation value texture using the following spin operators, where I is X, Y, or Z, and sigma I is the Pauli matrix. So this is the same spin operator as for a BDG Hamiltonian for a superconductor. And basically, you can then compute a skyrmion number in terms of the normalized ground state spin expectation value texture at each point in the Brillouin zone, where the integrand here, you could call it like a skyrmion curvature. And in the case of half filling, for the example I'm showing, you can compute this texture over the Brillouin zone, and it looks as follows. So above is the normalized spin, the X and Y components of the normalized spin. I'll just blow that up for you to give you a better sense of what's happening. Basically, you see the in-plane components winding by 2 pi. And below is the Z component. So you also see that it's winding. And indeed, we have a skyrmion of, say, charge 1. But what's really nice is, there are actually 10 different symmetry allowed Kronecker products of Pauli matrices at the 4-band level. So you can add various block off diagonal terms. And you can also fairly easily instead construct very physically relevant tight binding models for Brillouin-Bauer-de Hamiltonians at the 4-band level as well. So here is our Brillouin-Bauer-de Hamiltonian, written in terms of this normal state Hamiltonian var epsilon k and some superconducting gap function delta k. And the key point is this can become basically a 4-band model for a system with the C prime symmetry as well as a BDG Hamiltonian if the normal state is even in momentum, in which case C prime and C act in the same way on the normal state Hamiltonian. And then you can just add some superconducting gap function that is symmetry allowed by C prime. One example is spin triplet pairing with the following D vector. Yeah, basically you can then start to characterize the topology of even a simple model like this for a superconductor. You can, for instance, at half filling, compute the total Chern number and also the skyrmion number. And here I'm also showing the minimum direct superconducting gap, the middle gap, and also the minimum ground state spin vector magnitude over some portion of phase space. Here, delta naught is the superconducting pairing strength, and alpha is sort of like a hopping parameter. And so you already see some decoupling, basically, of the total Chern number and this spin skyrmion number. So here, for instance, the total Chern number is 4 and the skyrmion number is -2. And it looks like there's another region where the Chern number is -4 and the skyrmion number is +2. But actually, if you look at this plot of the minimum ground state spin magnitude, in these regions, the spin is actually 0 somewhere in the Brillouin zone. So the skyrmion number is not actually topologically stable here. It's forming what I call an almost skyrmion. It's like a charge 2 skyrmion, but with a hole in it. So this already kind of shows you another kind of decoupling, basically where you can have a total Chern number that's stable, but a spin skyrmion that's actually unstable. At this level, you only see the type 1 topological phase transition. Basically, there are too many constraints on the model to allow for the type 2. So that's just one example of the kinds of toy models, toy model block Hamiltonians that you can construct to study the 2-dimensional skyrmion phase. But what's really nice is that you can use this to construct toy models for the 3-dimensional skyrmion phase. The key point is the 2-band Chern insulator realized a baby skyrmion over the Brillouin zone, and we made use of that. But for the 3D case, we need a full skyrmion over the Brillouin zone, realized by our 2-band block Hamiltonian. And there is such a block Hamiltonian that can realize this. It's the block Hamiltonian describing the Hopf insulator phase, which is normally, understood in terms of like linking of rings of points, basically in the Brillouin zone. But actually, you can also visualize the topology of the Hopf insulator in the Brillouin zone as the formation of a hedgehog in your ground state spin or pseudospin texture. And so the key point is you can instead look at a 4-band model, including the Hopf insulator in this way, and you can compute the ground state spin expectation value texture, for instance, including a spin triplet pairing. And indeed you will, so this is the 2 different colors correspond to 2 different radii for spherical momentum shells in the 3D Brillouin zone. And basically, indeed, you see this full hedgehog forming in the spin texture for the ground state at half filling. So what's really nice about this is that we can bootstrap off of past work showing that the Hopf insulator block Hamiltonian with kind of unusual boundary conditions can realize unpaired Majorana zero modes. So the idea is that instead of that Hopf insulator Hamiltonian describing a system in 3 dimensions with a 3D Brillouin zone, we can instead replace the Z component of momentum by some angle theta that's effectively characterizing a defect in a 2-dimensional system. And then if we have open boundary conditions in X and Y, and also this, KZ replaced by theta, for instance, equal to arctan Y minus X, then when the Hopf invariant is non-trivial, you can realize, so this was done in this past work, you can realize an unpaired Majorana zero mode at the defect and another one at the boundary, but it's actually like localized at a particular point on the boundary corresponding to theta equals 0, which corresponds to the center of the hedgehog in the 3D Brillouin zone. So you can compare basically the 2-band model for the Hopf insulator with these boundary conditions to the case of the 3D topological skyrmion phase constructed from the Hopf insulator Hamiltonian with additional, say, spin triplet pairing. Basically you can see some very interesting differences. So in the case of the Hopf insulator, you have twofold degeneracy at 0 energy, the 2 Majoranas basically. In the case of the 3D skyrmion phase, you have 4 zero modes. Actually those modes are already localized, unlike in the case of the Hopf insulator, where out of the diagonalization, basically you get these states with some probability density peaking at the defect and at the boundary, and you take linear combinations of those to realize the unpaired Majorana zero mode states. And what's really interesting as well is if you plot the complex number entries of the wave functions, 0 energy wave functions in the complex plane. So just take each of those complex numbers for the wave function for these lattice models. And basically in the case of the Hopf insulator, at least at the boundary, at the defect, there's some pollution, I think, from theta not equal to 0, but at the boundary, you clearly see these complex numbers forming a straight line, which is what we expect for an unpaired Majorana zero mode, which is purely real up to some phase degree of freedom. In the case of the 3D skyrmion phase, instead, at least for the states that come out of the diagonalization at the boundary, they form a cross-like structure. So you have 2 cross-like states, for instance, at the boundary and also at the defect, but they're polluted in the numerics. And basically, different linear combinations of these cross states realize 2 unpaired Majorana zero modes that are also found in a low energy theory analytical calculation, one being purely real and one being purely imaginary. So basically, we're realizing Majoranas in a strange case where they are actually isolated from one another by a particular phase in the complex plane. And given the low symmetry of this, this model, this is quite striking because I told you that pi2 sp2n over un gave integer classification, but pi3 sp2n over un actually gives z2 classification. So just based on the topology associated with the projectors, we do not expect to have 4 zero modes in this case. We expect them to hybridize and start to drift away from zero energy if we only had topology associated with projectors. So what this is telling you is that there's some extension of the topological classification due to additional topology associated with spin, which also has pi3 sp2n over un, in this case, giving an additional Z2. So the classification is at least in this case, Z2 cross Z2.
Actually, I have a question. So,
yeah.
but in the case of the type 2 skyrmion, you mentioned that which does not carry the gameless transition.
Yeah.
So how do you explain the bulk boundary correspondence in that case? How do you argue? Because if there is no guaranteed gameless transition, then how do you know that there will be boundary state?
Yeah, so you can think about that type 2 transition as allowing you to basically like unwind the skyrmion that's ultimately projecting a lower dimensional system that is realizing this bulk boundary correspondence. So what's happening is you're effectively trapping a zero dimensional system as a result of the spin texture in the Brillouin zone. And then you can think about a homotopy group either associated with the full system or just with this defect that's being trapped by the spin. And this basically, so what can happen in the case of type 2 is you could, you could change the winding of the spin texture and lose your zero dimensional system, and therefore lose the non-trivial homotopy group associated with this zero dimensional system that was giving you these unpaired, well, in this case, these cross states. So how do I want to say it to you? Yeah, basically you'll lose your non-trivial homotopy group. And so it can make sense basically that you could lose these topologically protected states in that case without a gap closing.
Okay, I see.
Like naively, we would think, well, you would have to close a gap basically to lose these zero modes. But the point is, if you're completely destroying the homotopy group associated with the defect in that case, then like it's kind of like you're allowed to just have them like lose them basically without a gap closing. So the point is you use the spin texture to trap some lower dimensional system. And then you can think about a bulk boundary correspondence of that lower dimensional system trapped by the skyrmion. And the type 2 is for that spin skyrmion.
Okay, I see. So
yeah,
I should really more consider in terms of skyrmion trapped states.
Sorry?
I think I kind of get what you mean. Okay.
Yeah, you have to think about the topology of this spin texture, and then the topology of this defect that can be trapped by the spin texture.
Okay.
And it's the topology of the defect that can give you these cross states. And the point is, though, if you change the winding of the skyrmion, which could happen by type 1 or type 2, you could lose the defect, basically, in the sense that you could change its homotopy group.
I see.
And if you do that, you're no longer, it's like a topological phase transition as a result of changing the effective dimensionality of the system.
Okay.
Basically, because this is related to work by Teo and Kane. The idea is that if you have some defect in a system, you can think about it effectively raising the dimension of the system versus the system without the defect.
I see.
Like this 2D system without the defect, it's just two-dimensional. But with this point defect in the center of the 2D system, we have an additional angle theta that characterizes this point defect. And so now our system effectively becomes three-dimensional.
Okay.
Sorry, I'll keep going.
Okay.
Yeah, so I'll just briefly mention the second bulk boundary correspondence, which is, you can think about it in the following sense. So we can think of our block Hamiltonian with this generalized particle hole symmetry as describing some isolated system with some number of degrees of freedom, some spin degree of freedom, S, and some other degrees of freedom, S bar. And we could really think of dividing this into a spin like subsystem consisting of just the spin degree of freedom and some very small environment, basically consisting of the S bar degrees of freedom. And basically, we can then think about performing a partial trace over the S bar degrees of freedom and focusing just on this spin subsystem. In doing that, we reduce the homotopy group to basically the homotopy group associated with a two-band Chern insulator, but now it's like a two-band Chern insulator of just the spin degree of freedom and in an open system. And so actually in this case, we expect topologically protected chiral modes in the non-equilibrium steady state of this spin system that we may not have been able to observe directly in the full system as a result of the C prime symmetry depending on spatial inversion, and spatial inversion generally being broken by open boundary conditions. There's also the possibility of realizing the appropriate homotopy group without spatial inversion, but this is what I'm going to talk about today. So basically, this already gives us some idea of how to go about experimental detection. So first of all, we could try to use ARPES to just detect these k-space skyrmions directly, similarly to how we detect the spin momentum locking of Dirac cone surface states of a three-dimensional topological insulator protected by time reversal symmetry. Another possibility is to look for transport signatures of this non-equilibrium steady state of subsystems for, say, just the spin degree of freedom. Basically, you have to think about like ignoring some of the information in the system associated with the S bar degrees of freedom. And another possibility is to use like STM or probes like this to basically just study the local density of states in a system describing a defect and effectively realizing the 3D skyrmion phase. Okay, I want to tell you about the Strontium ruthenate model because it gives me a chance to tell you about the type 2 topological phase transition in greater detail. So I'll just schematically go over the model. It basically, in the normal state, has a spin half degree of freedom and a threefold T2G orbital degree of freedom, so X, Y, XZ, and YZ. It includes intraorbital hopping, interorbital hopping, non-negligible atomic spin-orbit coupling due to the 4D ruthenium ion, and an applied Zeeman field term. This is was included basically in this model considered by Masatoshi Sato and others, and I think first introduced by Manfred Sigrist and co-authors, and then also a chemical potential term and an orbital energy offset term. And importantly, this is an effectively 2D model with a mirror symmetry taking Z to minus Z. And so the matrix representation of that mirror operation is important for what I'm going to tell you about. So I write it down here. And then we include superconducting pairing, as has been done in the past for this model, basically spin triplet pairing, although I realize night shift experiments indicate that the spin triplet pairing scenario is not very physically relevant. But the key point here is this is a model that's decades old, and there is additional topology in this other topological phases in this model that we weren't aware of. So an interesting case that I consider is the high field phase, where in this past work, a suitable D vector in this case is this one. And in this case, what's interesting is the tight binding model has this generalized particle hole symmetry, and it also has a particular form of mirror symmetry for the BDG Hamiltonian, this tilde MXY minus. And this is important for the following reasons. So basically, if the normal state has a mirror symmetry such as the following, where MXY takes Z to minus Z, the superconducting state also has a mirror symmetry if the superconducting gap function is odd or even under this normal state mirror, in which case the Bogoliubov-Dugens Hamiltonian satisfies the following relation, where this tilde MXY plus or minus takes the following form. And basically, if you have the tilde MXY minus, it happens that if the full system has C prime symmetry, then each of the mirror subsectors inherits C prime symmetry from the full system. And then you can consider two interesting cases, at least, as a result of realizing these spin skyrmions in one or both of these mirror subsectors. So you can have a case where you have a skyrmion forming in just one mirror subsector, and in the other case, the skyrmion number is trivial. And this is basically a generalization of what I was already showing you, basically a case of like a single skyrmionic texture. So I call this the chiral topological skyrmion phase. And you can think of these as like generalizations, basically, of two-band Chern insulators. And then another interesting case is where you have a non-trivial skyrmion number in one mirror subsector and minus of that skyrmion number in the other mirror subsector. And so you can think of this one as a generalization of a quantum spin Hall insulator. If you think about the fact that you can construct a quantum spin Hall insulator from a two-band Chern insulator and its time reverse partner. I think it's really interesting to show you phase diagrams associated with this tight binding model for each of these mirror subsectors, where here I'm just using a parameter set that was used previously, for instance, in this Masatoshi Sato paper. And I'm tuning the atomic spin orbit coupling and the applied Zeeman field. These are two knobs that from our study of quantum anomalous Hall insulators, we would expect to lead to interesting physics, interesting topological phases. And so basically I'm showing you the total Chern number for half filling for each of the mirror subsectors. Above and below, I'm showing you the skyrmion numbers, basically. And so what you can see already here is that there are significant differences, basically, between the total Chern number phase diagram and the skyrmion number phase diagram. And perhaps most importantly, you can have cases where the total Chern number is 0 and the skyrmion number is non-zero, or where the total Chern number is non-zero and the skyrmion number is 0. So there is no proportionality necessarily anymore. There's much greater decoupling at this level. And another thing is that for the parameter set considered previously for strontium ruthenate, it's in the chiral phase. And for this tight binding model, if I hold the superconducting pairing strength constant while tuning the applied Zeeman field, which is not physical, right? As we increase the strength of the applied Zeeman field, we would expect to slowly kill the superconductivity. But I'm just, exploring phase space in a, at a preliminary level. And at this level, you can also see the helical phase, where basically you have a skyrmion number of 2 in one mirror subsector and -2 in the other. So it's at least possible in physically relevant tight binding models. So I think it's helpful to actually visualize the skyrmions that are forming in different parts of the phase diagram, first of all, although there's a lot to unpack from those phase diagrams. So I'm showing you for 3 points, alpha, beta, kappa in the phase diagram. So alpha is in the chiral region, beta is in the helical region, and kappa is in this very interesting region where you see a continuous phase transition. So I'll explain that at the end, but it relates to the fact that you could have a hole basically in your spin texture over the Brillouin zone as you tune through parameter space. Now I can tell you more about the type 2 topological phase transition. So if we plot the minimum direct gap between bands that are adjacent in energy and that are relevant to the topology, so the occupied bands or the superconducting gap, you see some interesting things. So basically this first minimum direct gap plot is the plot between the difference between the the band that's second lowest in energy and lowest in energy, or third lowest in energy and second lowest in energy, or the superconducting gap. And indeed, for the total Chern number, you see it can only change with the closing of, say, the superconducting gap. But if you compare these minimum direct gap plots to the skyrmion phase diagram, you see that there are some like lines in phase space across which the skyrmion number changes without any of these minimum direct gaps going to 0. So this is some numerical evidence basically of the type 2 topological phase transition. So I'll go through this in some greater detail. Let's consider a cut through...
Actually, we have a maximal 5 minutes more.
Okay, I'm almost done. So we can just set lambda equal to 0, and we can look at a cut through the phase diagram. We see the skyrmion number jumping from 2 to 0. If we zoom in on this, we see fluctuations as a result of slow convergence of the skyrmion number, but we also see the minimum direct gap does not close during this transition. If we look at the integrand of the skyrmion number close to the transition, we see not much changes across the transition, except for a neck that breaks here and here in the Brillouin zone. If we zoom in on that region, we see that the spin is actually going to 0 in magnitude through this transition. If we look at the normalized spin, it looks as follows. Basically, there are singularities being realized in the partial derivatives of the spin. Basically, because spin is not conserved due to non-negligible atomic spin-orbit coupling and an additional orbital degree of freedom, we are having spin going to 0, changing the skyrmion number without the closing of an energy gap. So just quickly, I'm showing you the spin texture through the transition. The key point is there are 2 features that are interchanged in the spin texture. So one, a feature where the in-plane components change sign, and another where the out-of-plane components change sign. The idea is that at the transition, they coincide, forcing the spin to go to 0 in magnitude. And we can understand their interchange as leading to a change in the skyrmion number just by thinking of a simpler 1D example, where we imagine exchanging such features in this 1D winding number case. Basically, this allows us to or it corresponds basically to a changing of the winding number in this simpler system from 2 to 0. I'll just quickly mention the non-topological phase transition. So basically, the idea was that 2 little skyrmions of charge 1 were basically forming, and there's a hole in the center, in the spin texture at the center of the Brillouin zone, and the 2 little skyrmions are just moving towards one another and disappearing through the hole. So the idea was just that throughout this transition, there was a hole in the spin texture, and that's why you get a continuous transition. But more generally, if the spin is finite in magnitude everywhere, the skyrmion number is integer quantized. All right, so this is like the last slide. Basically, the key point is the type 2 topological phase transition contradicts the flat band limit assumption. The idea being that you could do exactly that sort of deformation that I told you about, and the skyrmion number could change as a result of the type 2 transition. And this flat band limit assumption is very important in study of topological phases. It's used to connect the spectrum of the physical Hamiltonian to the spectrum of the entanglement Hamiltonian for diagnostic purposes. It's used for numerical computation of Wilson loops, basically to deal with the issue of gauge fixing that appears in that calculation. And it's also actually used to construct the 10-fold way classification scheme for topological phases of matter. And I won't go into the details, but for instance, the earliest instance that I have seen of the flat band limit assumption is from 1983, basically in this paper by Avron, Seiler, and Simon. So I'll just leave you with a summary slide and maybe quickly make one point. I think that going beyond the non-interacting regime, there are many cases where we have argued that in performing adiabatic deformations, we are guaranteed to not alter the topology of the system. I think a broader implication of this type 2 transition and the contradiction of the flat band limit assumption is that some set of those deformations may be able to change the value of a topological invariant. Yeah.
Okay, thanks for the nice talk, and we probably can get 1 or 2 questions. Actually, we have a question from Professor Wang Yao, who is the next speaker.
Yeah.
Thank you for the nice talk. So about this type 2 phase transition in non-interacting system, I wonder if the Chen number change or not.
It can't.
Yeah, Chen number does not change. Only the skyrmion
Chen number, the total Chen number changes with the closing of an energy gap. But this skyrmion number, which can be independent of the total Chen number, can change without the closing of an energy gap.
Yeah, I think that makes sense.
Yeah.
Thanks.
Okay, do we have any other questions from audience? If not, then okay, again, thanks Ashley for making very excellent talk.